I also want to join all the other speakers in thanking Gediminas and the organizing team for putting us this amazing conference and for the opportunity to show a little bit the work that we've been doing in Aalto in the group of Päiviturma about this topological bound states in the continuum of plasmonic lattices. So let me start by just explaining what are bound states in the continuum. So as the name suggests, these are modes whose energy is lies in the continuum of freely propagating modes, but actually due to symmetry they are completely decoupled from these freely propagating modes, and therefore they remain spatially localized. So these are solutions that are appearing in general wave equations, so from of course quantum mechanics, but also water waves, acoustics, and of course electromagnetism. So if you think of having just confining potential, of course you have all the sets of modes as a particle in a box, but then you can have all the outside free propagating modes which will give you the continuum, and you can have some as you can see here, some modes which are actually lying in the spectrum, so the energy is completely resonant with the frequency of all the other propagating modes, but they remain still localized. So in this sense, if you think of what is the quality factor of this mode, so if you think of the energy that can be stored in this type of mode compared to the losses, of course they will not radiate, they will not lose, they will stay there forever. So in principle, these are infinite quality factor modes, and therefore they are actually having a zero line width. So they, in the context of photonic crystals, there are works by Marin Soljacic's group where they have demonstrated that these modes are actually having a topological origin. So if you think of in-plane dipole, of course you can have some radiation that it's coming out plane, but then if you think of arranging these dipoles in a way that there is a destructive interference, then the radiation is prohibited. And actually what they showed is that if you look at what the polarization of light is doing in momentum space, then you can see that actually these modes are polarization vortices. So for instance, if you look at the polarization here, depicted by this arrow, so vertical polarization, horizontal polarization, and whatever, you can see that in general one has some polarization, but then nothing special happens. And then in your kx, ky space, you don't have any particular thing. And then this is associated with topological charge, which if you count what is the phase of the polarization vector, how it winds around a specific point, which is here the origin, kx, ky equals 0, which is the gamma point of the Brillouin zone, then you will have just a charge of 0. But then something happens if you create this type of vortex. So you see here actually that there are these horizontal and vertical polarizations that are crossing at this vortex origin. And then actually in here, what is the polarization that you assign to the mode? There is no way to determine. And therefore, this is why actually there is no way to propagate freely to the outside and to the far field. If you revert the orientation of your vortex, you have here you have, let's say, a topological charge of +1. Here you have the anti-vortex with a topological charge of -1. And then you can have also higher vortices, which more complicated structures. It's important to notice here that if you think of just how the polarization winds, you will see here that actually you have always two points across the topological charge point of the vortex center, and in here you will actually find two lines, and this is because just in the orientation of the polarization, horizontal, I mean, doesn't you cannot distinguish between a horizontal that it's oriented in a way or in another way. So you will always have, let's say, that you need to go around twice your origin in order to go back and to acquire the phase. So actually these are also very interesting states because as they have this vorticity, they can generate optical angular momentum. Due to the fact also that they are some topological protected vortices, you cannot really remove them in the system once you have created. So these are particularly robust and interesting. But also, since the quality factor in these modes are really high, they are really interesting also for lasing purposes, because they are better trapping cavity modes than the normal ones. And so they really provide a nice mechanism for observing lasing. Now, the system that we have in the lab is plasmonic lattices, so it's just an array of metal nanoparticles illuminated with light. So if you imagine to have these spherical nanoparticles shined with light, you will have the electron cloud in the metal, which is just driven at the plasma frequency. And so you have the localized surface plasmon, so which is this hybrid mode of the electron and the electron cloud and the light. But then what we do is that we arrange these nanoparticles into array, and there you also have the diffraction due to the fact that these are arranged in lattices. Therefore, the particles that we have in the system is actually surface lattice resonance, which is the hybridization of this localized surface plasmon and the sharp diffraction that is given by the lattice that we have. And this really depends on the lattice geometry that we use. So the way to observe the dispersive structure of these modes is actually to illuminate them with some light coming from at a given angle. Then this angle will actually generate some in-plane momenta, which will then drive the localized surface plasmon in each of the nanoparticles. And you really need to think that these nanoparticles are behaving like really oscillating dipoles, because you have these collective modes going on. And so these are dipoles that will emit basically in the direction that it's orthogonal to the associated dipole orientation. So here it's this mode of the incident light is then radiated in the other direction. And by changing what is the incident angle, you can have you can change what is the in-plane momentum, then observe the linear dispersion that it's here. So the linear dispersion is mainly due to the fact that there is high component of light mode in the system, but then at the gamma point here, there will be the more the plasmon component that will emerge. And these systems are nice because actually they are able to concentrate the light and the electric fields very close to the nanoparticle themselves, and actually in a sub-wavelength region. So the incident radiation is actually, the incident light has actually a frequency which is in the order of the distance of the nanoparticles. But then if you look at the hotspots, it's really concentrated really around the nanoparticles. So they are really, there is really a nanoscale confinement of the light. Of course, these structures can be coupled with some gain. By gain, I mean the solution of dye molecules that will provide some coupling, and so they can be brought to the strong coupling regime, and then into the lasing, where you have really the stimulated emissions, and also Bose-Einstein condensation was observed in the group. This type of plasmons. So now let me come to the core of what I wanted to discuss, and let me start by just telling you a little bit about the symmetries of this setup, because I told you that actually the modes that we are interested in, they come from a symmetry mismatch between the radiation and the mode that we actually have. And we discovered that the rotational symmetry of the lattice is actually what matters a lot. So you need to imagine that each nanoparticle behaves as a dipole, and then you can think of, okay, then what are the modes, like the normal modes that we can have in general dipoles? For instance, if we consider a C2 symmetry, just considering systems that are invariant under rotation of 100 degrees, and you have just two particles, then the dipoles have only two ways of oriented. You have the aligned dipoles, which are oscillating in phase, and the dipoles that are oscillating out of phase. And I am putting them on this unit circle according to the phase they acquire when I rotate them. So this will acquire no phase if you rotate them, and this will acquire a pi phase when you rotate by 180 degrees. You can go on with the C3, C4, C6. So as you can see, every time you add another fourfold rotation, you have that there are modes that are actually doublet. So here in the C4 rotation, you have two modes that are just one 90 degrees rotation of the other. And in here you have another two sets of doublets. And according to the group theory, these are all modes that are classified according to what is the phase that they acquire under rotations. And this phase is actually given all by the phases on the unit circle. Now, this is a long story to arrive at what type of polarization vortex can all of these modes actually generate into a structure. So we discovered that there is a simple formula for that, and actually the charge that you can have will depend on the phase that it's on the irreducible representation table. So for each symmetry, you always have some mode, which are the A mode, so the one that actually when you rotate by the symmetry do not acquire a phase. Actually, they will always have a topological charge of +1. And then all the others. So in this talk, I will focus on the C4 symmetry and on the C8 symmetry. So you will see actually a topological charge of +1, -1, and -2. So let's start with the C4 symmetry. And we studied a system which, so it's a square lattice, but where the unit cell is actually complex because it's, again, a square array of nanoparticles. So these are all the possible modes that you can have in the system. So if you think of the dipole orientation and take into account the fact that these dipoles are coupled differently than these dipoles, then these are all the sets of modes. And these are classified according to the irreducible representation table. So we have two A modes, two B modes, and then the doublets. So this is actually the finite element method simulation. So you show the in-plane electric field and the out-of-plane electric field. So you see that there is a set of mode that is mainly in plane and a set of mode that is mainly out of plane. And notably, these two modes really, they are just the coherent dipole oscillation of all the nanoparticles and all the unit cells. Now, keep in mind that we are interested in modes that are emitting at the gamma point. So we will look only at vertical emission. And so we wonder what happens with the vertical emission of all these modes. So we studied that and we put that in momentum space. And since these polarization vortices, you need to really have change when you have your polarization. So here we should filtering of the emission in momentum space by filtered by the corresponding polarization. So you see here that this particular mode, if you think of how this winds around the origin, you can see that these are just two dots of horizontal polarization and then rotates into two dots of vertical polarization. And then overall, there is a phase acquired, which corresponds to the topological charge of +1. Then you have the dipole, the boring dipole mode, I call it, because it just doesn't respond to any type of polarization, and then the charge is 0. And then the other mode, which has the opposite vorticity. Now, we have all these modes, and they are all at the gamma point. So how to when we studied in the experiment and we brought the system into the lasing regime, we observed lasing, like when we increase the pump fluence, we see a nice threshold curves. And these are all the modes that I showed you before in the dispersion. And we only see one of them lasing. So actually, this is the real space configuration of the lasing mode. So how to identify which is the one that it's actually lasing? And so polarization resolved measurement. So what we did is that we looked at the real space emission polarized along the horizontal, vertical, and all the possible direction, comparing with the theory interpretation. We have done for all the modes, but this is the only one that was matching. And actually, if you think of how this unit cell is projected when we filter the horizontal polarization, then you see that there is some interference effect in the bulk, but then builds up in the horizontal axis. And yeah, the agreement that we see is, I would say, pretty good. Then what we did is that we also studied the C6 symmetry. So we had a triangular array, and now the unit cell is composed of 6 particles. And what we did here is that we also changed what is the size of the hexamer. So we built a lot of samples from 50 nanometers, so hexagons that are very small, to very large hexagon. And we see each of them lasing, but with a different threshold and with a different intensity, with a different frequency. So this is a clear indication that there is something going on, because the mode is not the same in here. And actually, this is just the theory representation of how the corresponding modes at the gamma point will show. And actually, you should compare it with the experimental results. So we see actually that each of this sample is lasing into bounces in the continuum, which has a different topological charge. So it seems that there is some phase transition that is induced by the fact that we are changing the lattice. But actually, what is happening is that we calculated with this the quality factor of each of these modes, because from the theory perspective, we know we can calculate what are the energies. So we have the imaginary part and the real part of each of the modes. And we see that these modes change a lot, imaginary and real parts. So the losses of these modes in particular, because it's associated to the imaginary part, changes a lot when we change the structure of the system. And so summarize here with the quality factor, so the real part over the imaginary part, you see that actually there are, each of these modes have, as a function of the this hexagon, like how they're big, they cross. And we see that in the regime where this mode, which is the B mode with topological charge -2, has the largest quality factor, this is actually the one that also in the experiment was the lasing mode corresponding. And then we have almost a one-to-one correspondence, except for this very tiny region over there, where we actually believe that there is a mode competition due to the gain and the structure of the mode. So actually what we, at least in this part, we have that the mode with the highest quality factor is favored for lasing. So essentially we have that there is a transition in the topology of the lasing mode, which is driven by the fact that there are these crossings in the quality factor. This is something that is not standard in topology, because in topology, usually you are associated with phase transitions, so changes of the topology of your ground state, but due to the closing of gaps in energies. But in here, there's the quantity that is associated is also the losses. So there is a highly non-emission effect over here. And the fact that this is due to the losses is also indicated if we look at what is the spatial part of the mode. So here we show the finite element simulations for the parameter where the lasing mode was the B prime, so this one here. And in this lower set, the lasing mode was the A prime. And if you look and compare the lasing mode, so the winning mode, compared to all the others, which are the loser mode, you can see that actually the nanoparticles are the furthest away from the hotspot. And this is because even when they have a hotspot on the nanoparticle themselves, there will be strong ohmic losses, because I remind you, these are metallic nanoparticles. So the lower losses will have the higher quality factor, and then will win for the saturation of the gain. So this mode will win over all the others for the gain, and this other one will win for all the others of the gain. So here I come to my conclusions. So I've shown you that actually with engineering lattices with complex unit cell, we can play around with the plethora of modes which are bound states in the continuum, so polarization vortices associated with different topological charges, and we are able to lace into them, and we are actually also able to select, in particular, the mode that we will win for the mode, and we have seen this via topological phase transition, which is driven by the losses. So I want to acknowledge the team. I'm the theorist, but actually there is, as you have seen, a lot of experimental work. Kertu and Rebecca were really the main one in the lab. Tommy also was supervising all the work, and then from the theory, Christian did a lot of simulations for this. A second part, and also Javier for the finite element simulations, and Päivi Torma, of course, will supervise all the work. But just let me tell you that actually the team has also another part of the group is working on flatband and superconductivity. So for that, you should refer to Ville here, who had a poster yesterday. But thank you for the attention.
Okay, open for question. Yes, please.
Thank you, Grazia. You're also breaking translation invariance, which should give another mass. So did you take it into account in your group theory analysis?
I'm breaking translational invariance. What do you mean? No, because...
So your C6 lattice has intra-unit cell bonds and inter-unit cell bonds.
Okay. These systems do not obey tight binding at all. Yes, but there is very long range coupling. So everything is coupled with everything, and we estimate that to be a very small contribution. And actually, all the finite element simulations are done by assuming that we can do everything on the unit cell, because we can still have the unit cell, and the unit cell is replicated. So there is still translational invariance in this sense. You're not convinced of that? We can discuss later.
More questions? Maybe I have one.
Yes.
How to measure the topological charge directly?
So we measure it by looking at this polarization winding. So actually by counting how many times you have this winding when you rotate your polarizer filter in the experiment. So this is the way we measure, but there is also other ways to calculate really from that is more from the theory point of view, to calculate this winding of the polarization vector.
Okay, thank you. More questions? If not, case, thank Grazia again.
Yes, thank you.